Okay, let's get started. So let me start with a few announcements. So assignment 4 is due on Friday. The exam is on Friday the 12th of December. The rooms are still to be defined. Let me make a note about the exam. So it's 2 hours in length. It'll probably be choose n-1 out of n problems. I still have to finish writing the exam. You will be allowed to bring 5 pages of handwritten notes. Letter size. I found it hard that you would be able to write more than 5 pages anyway. Okay? So you're allowed to bring in with you 5 pages of handwritten notes. And you can write down whatever you want on those notes, obviously. And there will be a formula sheet provided as well. So someone will memorize any formulas or anything like that. No, 5 pages total. So, 2.5 pages. It's double-sided. Okay. Any other questions about the exam? Yeah, I would say it's comprehensive on the whole course, yes. Oops. Covers all chapters that we have done in class. And we also note that the full textbook, I guess the textbook should also be in quotation, is online. So I made a PDF file of the whole textbook, and I put that on the website. It's in the first section of the Moodle course. I think it's just called Full Textbook. I changed the font a little bit, so it's a little bit smaller. It takes less pages. And it has some extra problems, and I fixed most of the typos. Except there's still that one problem with the Noether's theorem that's not resolved. How many problems on the exam? Currently, it's choose 5 out of 6 problems. Okay. Any more questions about the exam? Okay. And then Monday, 8th of December, we'll have a review session. starting at class time, but it will last as long as people have questions. Now I have to note that I might be a couple minutes late. I hope not, but I have an appointment that I have to go to at 9 a.m., so hopefully it's done in 2 hours, but otherwise I might be a few minutes late for this review session. But I specify that it'll go as long as it takes in case you want to go into a classroom, and that classroom, has another class after my class. Maybe that's not the best idea. Okay. The exam, I don't know, I guess it only concerns Michelle, but the exam will be, at School of Mines or at USD, so you'll have to make your way there once Connie finds a room. Okay. Any more questions? Okay, so today should be a pretty light lecture, and we'll do sort of the final topic on, I sort of promised you the whole time that we were doing this very theoretical version of classical mechanics to gain some insight into quantum mechanics. So that's what we'll cover today. So let me just quickly do a summary of what we did last time. Last time we introduced action, angle, variables. Okay. So the action variable we called Ji, and that was given by the integral over a period of the momentum integrated over the coordinate variable. Okay, so this is for periodic motion. Periodic separable motion. And what we found was that the Ji equal constants. In fact, they were the equal to the canonical momenta in an extension of the Hamilton-Jacobi method. And then we found that we could write the Hamiltonian as a function of our coordinates and the Ji. We also introduced the angle variables, which we called lowercase wi, and those were given by di w, uppercase W by di Ji, where W, uppercase W, is equal to the generating function of transformation, these WIs were called angle variables. And the whole point of all this was that once we'd rewritten the Hamiltonian in terms of the QI and the JI, we found that these frequencies, nu I, were given by the partial derivative of the Hamiltonian with respect to the JI. And that was the frequency of motion for the coordinate QI. And this was very interesting because it allows us to understand the frequencies in a system without having to actually solve the equations of motion for that system. So this action angle variable sort of uncovers the fundamental frequencies in a mechanical system. Okay. Any questions about that? Okay. So today, we'll look at the connection to quantum mechanics. So this whole Hamiltonian description maybe is not the most straightforward for describing a system in classical mechanics, because usually the Lagrangian is more straightforward to write out and directly gives you the equations of motion. However, the Hamiltonian is connected to the energy, and it's also directly used in quantum mechanics. And so uncovering or understanding how to do classical mechanics with the Hamiltonian is important because it gives you an understanding of how you go from classical mechanics to quantum mechanics. And it makes it a little bit less arbitrary how you go to quantum mechanics. So I think all of you have taken quantum mechanics or are taking quantum mechanics. But let's remind ourselves of a few key points about quantum mechanics. So recall, for quantum mechanics, a system is described by a wave function which we often label with the ket psi. The observables, so things that you can measure, are obtained by operating on the wave function. Sometimes we call the wave function a state vector. That would be the Heisenberg way of calling it. Alright, so my tablet's going crazy. I might have to restart it. I'm going to try a trick, according to the internet. I might have to restart my tablet here. Oh, this is really annoying. Okay, I'm sorry. I'm going to have to restart my tablet because it's gone crazy. I'll be back in like a minute. Okay, so hopefully no any more problems. Seems to be if you try to charge the tablet at the same time as using it, it goes crazy. Alright, so as I was saying, in quantum mechanics, a system is described by a wave function or a state vector, depending on if you're doing Schrodinger or Heisenberg. The observables, so things that you can measure, are obtained by operating on the wave function. So for example, if you want to measure x, you have to take the operator for x, and that will give you, as an eigenequation, the value of x for the observable of the wave function. Okay? Operators do not commute. In general. So that means if you want to measure x and then y on a system, you won't measure the same thing if you instead measure y first and then measure x. Okay? And then we have two ways of doing quantum mechanics. So in the Heisenberg way, the state vector is constant in time and the operators depend on time. And the fifth point is that in the Schrodinger formalism, the operators are constant and the wave function depends on time. Okay? And much of the early parts of quantum mechanics, historically, has been to show that 4 and 5 really lead to the same description of the world. Okay? So I'll take these as given, these points about quantum mechanics that you guys know from your quantum mechanics courses. So let's look at a few connections between what we've done in this course and quantum mechanics. So the first one is Poisson brackets, which is the classical mechanics thing, and commutators, which is the quantum mechanics equivalent. So we notice a lot of similarities between Poisson brackets and commutators. And so there's a prescription for going from classical mechanics to quantum mechanics. And that's called the canonical prescription. to go from classical mechanics to quantum mechanics. In the canonical prescription, so remember we showed that in classical mechanics you can do a lot of things with Poisson brackets. Right? They're related to transformations and symmetries, and they also give you how things evolve with time. Right? The Poisson bracket of something with the Hamiltonian is the time evolution of something. So the canonical prescription to go from a classical mechanical description to a quantum mechanical description is to replace, anytime you have a Poisson bracket of two, in classical mechanics we call them functions, in quantum mechanics we call them operators. So you take the Poisson bracket of the two functions and you replace that by 1 over IH bar, and then it becomes the commutator of the two quantities. So commutator, so known as. Okay, so you replace the functions by operators, and you replace Poisson brackets by commutators. So recall, in classical mechanics, the total time derivative of some function was given by the Poisson bracket of that function with the Hamiltonian plus the partial derivative of that function. That means in quantum mechanics, the time derivative of some operator, which I'll call f hat, is given by, now I have to replace the Poisson bracket by 1 over IH bar, and then the commutator of that operator with the Hamiltonian operator. And this is what you get. In the Heisenberg formalism. So this is in fact the most general, complete prescription for going from classical mechanics to quantum mechanics. It is this one here, the replacing Poisson brackets with commutators. We're going to look at two other ones that are not as complete as this one. Okay? So there's a connection between the Hamilton-Jacobi equation and the Schrödinger equation. Between the Hamilton-Jacobi equation and the Schrödinger equation. So consider the time-dependent Schrödinger equation. Time-dependent Schrödinger equation that you can write as Hamiltonian, which depends on Qi, Pi, and T, times the wave function is equal to I H bar times the time derivative of that wave function. Okay, and the Schrödinger equation is like this, where the PI's are given by h bar over I di by di qi. Alright, so think of the x momentum is given as a di by di x, right, times h bar over I. So this Hamiltonian function that depends on the q's and p's, or the x and px's, typically is going to have a kinetic energy term in it, and that kinetic energy term is going to have p squareds in it. And so anytime you have a p squared, you're going to have a di squared by di qi squared. And so indeed this is a way of writing the Schrodinger equation where, if you recall, one of the peculiarities of the Schrodinger equation is that the derivatives are second order in the coordinates and first order in time. Whereas for maybe a wave equation of, sound wave or something like that, the derivatives with respect to the coordinates are second order, and the derivatives with respect to time are also second order. So the peculiarity about the Schrodinger equation is that it mixes second order derivatives in the coordinates with first order derivatives in time. Okay. So that's the time-dependent Schrodinger equation, TDSE. So consider a solution. We call this a plane wave solution to the time-dependent Schrodinger equation. So plane wave solution means that we can write it as the wave function psi is equal to some amplitude times e. I'm going to write this as e to the I over h bar, and then some function s of the coordinates in time. Okay, so then the momentum operator, pi, which is given by h bar over I di by di qi of psi, if I take that derivative, I'm going to get h bar psi times di s by di qi. So anytime I have a pi in the Hamiltonian, I can replace it by an h bar psi di s by di qi. Right? So now if I look at the other side of the Schrodinger equation, if I want to do I h bar di psi by di t, then looking at the form that I have for psi, I would get minus h bar psi times di s by di t, just applying the chain rule. Okay, so now if I put this into the Schrodinger equation, so that's the one I have up here, right? H of qi and pi and t times psi equals I h bar di psi by di t. So I can write h, instead of depending on qi, pi, and t, I can write h as depending on qi, di s by di qi, and t. Right, because the pi we just wrote as di s by di qi. So if I write the Schrodinger equation, I have h, which now depends on qi, di s by di qi, and t. times h bar psi, that's equal to the IH bar di psi by di t, which was minus h bar psi di s by di t. If I rearrange this and put it all on one side and factor the h bar psi, I get h of qi di s by di qi t minus di s by di t times h bar psi equal to 0. Now, this of course has a trivial solution of the wave function being 0 at all times, but if the wave function doesn't equal to 0, which of course is a non-trivial solution that you want, then you get that the third thing in parentheses, so hqi di s by di qi and t minus di s by di t equals 0. And that's exactly the Hamilton-Jacobi equation. So the Hamilton-Jacobi equation in classical mechanics is connected to the Schrödinger equation in quantum mechanics, where the action in classical mechanics, S, is the phase of the plane wave solution in quantum mechanics. Question?
Yeah, you had a minus sign on the right side of that equation, and then, pardon me?
That's right, that should be a plus.
Oh, okay.
You're right, that should be a plus. Okay, so that's already two connections between classical mechanics and quantum mechanics. One is the canonical prescription, which always works. That's the Poisson brackets go to commutators with an IH bar in there. And this is now the connection between the Hamilton-Jacobi method and the Schrödinger equation. And what you should find is that when H bar goes to 0, that's how you go smoothly from quantum mechanics to classical mechanics, right? The whole point of quantum mechanics is that H bar is not 0. So when you zoom in to the tiniest scales, stuff is usually quantized in units of H bar. And if H bar becomes 0 in that limit, then stuff becomes continuous. And that's how you get this smooth transition between quantum mechanics and classical mechanics. So the final connection that we're going to look at here is in fact historically the first connection that was made. And that's the Sommerfeld and Wilson prescription. So historically, this was the first way that was found to connect quantum mechanics to classical mechanics, but it's incomplete in a sort of what we call now the old classical mechanics, before Schrödinger and Heisenberg sorted things out. Okay, so the Sommerfeld and Wilson's prescription is based on these action angle variables that we talked about earlier, and particularly. The Sommerfeld and Wilson prescription tells us that the action variables must be quantized in units of Planck's constant. So we write that as Ji, remember, the action variable, which is given by the integral over a period of pi dqi, the prescription is that that must equal to n times Planck's constant h. Okay, so this is already intrinsically limited to systems that are periodic. But most systems are periodic, right, in quantum mechanics. Think of black body radiation. They're all a bunch of little simple harmonic oscillators. The simple harmonic oscillator itself, right, applies to a variety of things. Many of the wave functions, have plane wave solutions that might be sine waves, so they're periodic as well. The atom is periodic, like electrons going around the Bohr atom. So there's a lot of systems that are periodic, right? So it is a fairly general prescription. So if you remember in the example 8.6, we looked at a simple harmonic oscillator in classical mechanics. That was example 8.6, I believe. And in particular, what we found was that we could write this action variable. So we did an example in 8.6 where it was a two-dimensional harmonic oscillator. And of course, the result's the same for a one-dimensional harmonic oscillator. So we found that this J, the action angle, action variable, was given by 2 pi alpha times the square root of m over k, where alpha was the total energy. So you can go back in your notes and look at that example. Part of the procedure involved us relating the action variables to the alpha, the constants. In this case, we recognized that the constants alpha were equal to the energy, and then we found this prescription. So the Sommerfeld-Wilson prescription requires us that this, J, must be equal to n times h. So I can rewrite that now isolating the alpha, which is equal to the energy. So that's going to be 1 over 2 pi square root of k over m times h, or times n times h. And so I have a h over 2 pi, which we call h bar, right? So if I put that simplification in, and omega is the square root of k over m, then I find that this is equal to n h bar omega. So I apply the prescription of Sommerfeld and Wilson that the action must be quantized in units of Planck's constant. And I know the action variable in terms of the energy, alpha. And so I find that the energy is equal to n h bar omega. Of course, that's the solution that you find to the simple harmonic oscillator in quantum mechanics. That's the quantum mechanics solution to the simple harmonic oscillator for the energy levels. And the only hiccup here is that there's a ground state energy, right? That's not zero. And of course, this prescription doesn't give you the ground state energy. So it gives you all the other energy levels, but it doesn't give you the ground state energy. So it's incomplete. That's why this is not the best way to do classical mechanics or quantum mechanics. It kind of works, but if you go into really the details, it breaks down. Okay. So let's do one more example here. let's do the Sommerfeld-Wilson prescription again. For a particle in a central potential. So, for example, gravity or the Coulomb force. So the action variable, so if we have a problem, the potential would go something as a constant over R, right? And so we would find that in spherical coordinates, we would find that phi is cyclic. All right, so think of a planet orbiting the sun. That's actually a two-dimensional motion, right? The radius changes, it's an elliptical orbit, and the angle theta in the xy plane, if the motion's in the xy plane, the angle theta changes, right? So you could specify the position of the planet using theta. I inverted the definition of theta and phi. But basically you need a polar coordinates in a plane to define the position of the planet. And angular momentum for that orbit is conserved, right? So angular momentum points in the z direction. And so the total angular momentum must always be conserved. So that's the relation between phi and r. Okay, so because angular momentum is conserved in the z direction, then the motion must be planar. So we can write the action variable j psi, the one that corresponds phi, the one that corresponds to p phi d phi. We know that p phi is the z component of angular momentum. So if we integrate over one orbit from 0 to 2 pi, we have the integral of Lz d phi. So phi is actually, sorry for being confusing here, but phi is really the correct thing. So this is our orbit. And so we have r and phi. All right, so phi is cyclic because the potential only depends on r. And so the momentum of the generalized momentum in the phi direction is conserved. And we call that, or we've already done the math to show that that is the z component of angular momentum. And so angular momentum is conserved, and it's equal to Lz. Okay? So the action, so Lz is a constant, right? So if I do this, the action of the phi variable, then Lz can go out of the integral, and I just get 2 pi Lz over one period. Sorry for being confusing with the explanation. So if we apply the Sommerfeld-Wilson prescription, this must be equal to n times Planck's constant. And so what we find is that the z component of angular momentum, Lz, is equal to n times h over 2 pi, which is h bar. And so of course that's what you have for quantum, in quantum mechanics. When you have particles, for example, the electron orbiting an atom, the nucleus of an atom, the z component of the angular momentum is quantized to be n times h bar. Right? That's the Bohr atom, basically. That's why it's the old quantum mechanics. Now, again, the comment here, how the Sommerfeld-Wilson prescription breaks down, is that in classical mechanics, in this exact scenario, the total angular momentum is equal to L, Z. So total angular momentum for this planet orbiting the sun is in the Z direction, and so L is equal to LZ. So you might be tempted to wrongly conclude that in quantum mechanics, the total angular momentum is quantized. But that's wrong, right? In quantum mechanics, it's the projection of the angular momentum about a certain axis that's conserved, that's quantized. Okay? So L is not quantized. Even though in this example, instead of calling LZ, I could have just called it L because L is in the Z direction. But then we come to the wrong conclusion. So that's why the Sommerfeld-Wilson prescription is not perfect. Let's do one last example here. So let's consider the case where the energy is equal to the Hamiltonian, and it can be expressed in terms of the action variables. And so the action variables must be quantized. So that means the energy can be defined as a Hamiltonian, and by specifying a bunch of quantum numbers, where we've quantized the action variables. So consider the case where the energy is described by a set of quantum numbers. And I, that quantize the action variables. So consider the change in energy. When one of these action variables changes by 1 unit. By 1, let's say, quantum. So what I mean is that one of the J's goes to what it was equal to plus h. So the change in energy, delta E, is going to be the new energy, which is h, J1. One of the Ji's has an h, minus the Hamiltonian without the change. So the change in energy from one of the action variables increasing by one quantum. So if we do a Taylor series, of the first term, h evaluated at J1, Ji plus h, and Jn, that's roughly equal to the Hamiltonian evaluated from J1 to Jn plus di h by di Ji times h. All right, so then the change in energy, if I subtract h, the Taylor series that we just did, and I subtract the unvaried h, then I find that delta E is simply given by di h by di Ji times h, Planck's constant h. But recall that the frequency associated with that action variable was actually equal to di h by di Ji. So that means that the change in energy, E, is given by nu I times h, where nu I is the frequency associated with Ji, or little qi if you want. And so that should look familiar as well. The change in energy from going from one quantum state to the next is given by the frequency of that state times h constant, the Planck's constant. So that's exactly the Bohr atom. All right. Remember the Bohr atom, where you look at an electron orbiting a nucleus, and you quantize the z component of angular momentum, and then only certain orbits for that electron are allowed. And you find that the change in energy associated with those change in orbits from going from one quantized angular momentum to another are given by the frequency nu times h. And that's in fact how you find the frequency of the light that's emitted in going from when an electron jumped from one orbit to the other. Okay, so this Sommerfeld-Wilson prescription is what we call the old way of quantum mechanics. It's like it works with the Bohr atom. Of course, we know the Bohr atom is not technically correct, right? The Bohr atom is a big oversimplification of what's going on. And so I'm sure you've done in the rest of your quantum mechanics courses, the Schrödinger and Heisenberg, and hopefully a little bit of history into how it all fits into the big picture. Okay, so that's about it. This covers the material I wanted to cover for this course. Like I said, I put online the full version of all the notes, and it has 2 chapters that we didn't do in class. I don't remember the numbers of chapter. One is the chapter on applications of the Lagrangian, so I encourage you to read it, but I won't test you on that material. There's 2 main applications. One is figuring out the orbits in a central potential in much more detail, and it derives the elliptical orbits and things like that. And the other application is oscillations and coupled oscillators, or systems of coupled oscillators. And the final chapter that we didn't get to is the transition between classical mechanics that we've done now and what we call field theory, or the theory of fields, which is the classical mechanics of continuous systems. We've only looked at individual particles that had a continuous coordinate, or individual coordinates for each particle. In continuous systems, the coordinates themselves, or there's an infinite amount of particles, basically. So like the vibrations of a string, each position on the string is like a different particle, so it's a continuous thing. And so the formalism for that is introduced in the last chapter, which I encourage you to read for your own education, but it won't be tested on the exam. Okay, so any questions about this or the rest of the course or the exam? Okay, well, if there's no questions, I'll talk to you all on Monday. Remember that I might be, hopefully I won't be, but I could be a little bit late. And you should come prepared with questions, but otherwise I'll do a set of example problems that may or may not be representative of what's on the exam. Okay,